Recording. Okay, great. So we will continue the particle swarm optimization. We already started the discussing the introduction to the technique and the basis of this technique. We will discuss also some definitions, or we define some terms in the particle swarm or in swarm intelligence in general. And we will see the algorithm, how to proceed from the initial population, creating the offspring, and then end up with the global optimal solution. Initialization and velocity update. As we mentioned, we have here particles, and these particles has position and the velocity. So based on the position of the particle and the velocity, the particle can explore new locations or new areas in the search space. So we will see how to update the velocity of each particle, and then how to update the position of the particle accordingly. And the stopping criteria, as usual, and these are criteria to stop the search. And we will see also the key parameters of this technique. So in order to wisely set these techniques to get better performance. BSO, late 90, professor engineering and a professor on social science. And as we mentioned, in this technique, based on swarm behavior, based on it is extract the principle of learning process, and each one can learn from his own experience and from others' experience. So we have some cognition part, and we have also some social part in this technique. So this technique balances between the local and the global search. And as we mentioned, probably, we covered this part. And the BSO is characterized by simple in concept, easy to implement, and computationally efficient. And based on my own experience, and also you can find this also in literature, that BSO outperform the genetic algorithm. You can have in few iteration, and you can end up with better quality solutions. BSO has a flexible, well-balanced mechanism to enhance global and local exploration. We will see this in details later on when we see the steps of the technique. Of course, BSO is a population-based. You can also list the advantages of population-based technique in terms of implicit parallelism, in terms of less susceptible to be trapped in local optima. Each particle represents a solution, and these are some of the stopping criteria that you can set the best solution doesn't change for a long time, or you reach to the maximum number of iteration. The BSO system combines social and the cognition part, as you mentioned earlier. This is using this. Unlike GA and the others, BSO has a flexibility to balance between global and local search. Local search or local exploration comes from you learn from your own experience. So so you learn from your own experience here. This is the cognitive part. And the global, this is the social part. Okay. Overcomes the premature convergence problem and enhances the search capability. We already covered this. By collaboration, you can get better results and you can move forward. We all covered this part. So I think BSO definition, we stopped here, right? But even we have some explanation here. A particle is a solution, and it is a vector with the m-dimensional, where m is the number of optimized parameters. So we covered all this. Population is the number of particles together, and this is the swarm also, called the swarm or population. We covered this. Particle velocity, and again particle velocity, the m-dimension vector, real valued, as we mentioned. We have maximum, we limit the velocity of each particle with the maximum velocity. So the velocity of the particle must be less than or equal Vmax, and definitely there is a velocity in each dimension, and definitely this is Vkmax. So the velocity of the particle is within between minus Vmax to Vmax in this dimension. And this resemble the learning process. And you cannot find over the night a big change in learning of a person. Learning process is slow with time, grows with time. Riyad Al-Aqili needs one of you to send him an invitation. I don't know what is the problem with him. So please, anyone can send Riyad Al-Aqili invitation. So this limit enhances the local exploration and the space of the realistically simulates the incremental change in human learning. The maximum velocity in each dimension is characterized by the range of kth optimized parameter and given by the following equation. This is Vmax in any dimension, and dimension of k or T1 or T2. Considering that example, you know the k between 1 and 100 NASA, for example. So this is the maximum and minimum. So velocity, maximum velocity the dimension of k is 100 minus 1 over n, and the n is the number of intervals that you can set. For example, n equal to 10. So I divide the range to 10 intervals. So the maximum velocity could be approximately 10. So if you have k equal to, in one solution, if you have k equal to 20, so this 20 can move up to or lower than by 10. 10 is a maximum, and this 10 is, this is the maximum limit. This 10 is multiplied by a factor here, which is less than 1. And if you assume that it's a random number, so this could be 0, this could be plus 5, this could be minus 2, minus 3, any number between plus minus 10. So this is the movement of the particle at that position. So you have also maximum velocity for T1. If you have here a solution K T1, T2, you are optimizing the parameters of the controllers. So you have also a velocity here of T1 maximum. So this is equal to, and so on, n equal to 10. Maximum minus the minimum. This is probably 1 second, and the minimum is 0.0 second, 0.1 second. So you can get the velocity in each direction, and you limit the velocity of the particle within these bounds. And the chosen number of intervals, and you can set 10, for example, works fine. N also equal to 10. This is from my own experience and others also. N equal to 8 is also a good compromise. Of course, you have to compromise here, لأنه if you make n equal to 100, for example, so you are limiting the change in the position of the, and you are limiting the velocity. Now, velocity maximum will be 1. So for any particle here, the movement of the particle will be very limited. Okay, so this is if n is very high. If n is very low, 2 for example, that means you can allow for a particle here to fly going to the other direction, very far position, which is not healthy. It becomes, at that time, it becomes like a random search. So one, you need, the swarm behavior. All are progressing towards a certain objective, not flying from here to there. So you need to compromise for n. As we mentioned, n equal to 8 or 10, they are working fine. The inertia weight. This inertia weight represents the relation between the updated velocity with the current velocity. So we have to update the velocity from one iteration to another. So the relation between the updated velocity or new velocity with the old velocity is related by what we call the inertia factor. It is a control parameter that is used to control the impact of the previous velocities on the current velocity. So it influences the trade-off between the global and local exploration capabilities of the particle. And for initial stages, the search process, large inertia weight to enhance the global exploration is recommended. And at the final stages, this inertia becomes very low. So we are enhancing, at the beginning, we are enhancing the global acceleration. Now at the final stages, we need to enhance the local acceleration. So this inertia will be decreasing. Conversely, for the last stages, the inertia weight is reduced for better local acceleration. We will see how to this inertia weight will change or will reduce from one iteration to another. The decrement function for decreasing the inertia weight given as omega of t, or the inertia W of t, equal to alpha multiplied by W of t minus 1, the earlier value of the inertia. The updated inertia equal to alpha, where alpha is less than 1. Alpha is less than 1, but very close to 1. يعني we can set alpha equal to 0.95 مثلا, or 0.9 حتى even. If we set it 0.9, so omega or W at iteration 2, if t equal to 2, equal to 0.9 W of iteration 1. And the W of iteration 3 equal to 0.9 W of iteration 2 and 0.9 W of iteration 1, and it becomes 0.81. So this is the weight. Now it becomes, and if you set it here, for example, if you set this as 1, so 0.9, 0.81, 0.72, and so on. So omega is decreasing as such. So this function can be used to update the inertia from iteration to another. T is the iteration number. This is the iteration number. Okay, there is another decreasing function also for W to update it from one iteration to another. Over the maximum number of iteration, you can say, I will set, for example, W max to 1.2 مثلا, and the W minimum equal to 0.4. These are typical values, by the way. And also a number of iteration, I will set a number of iteration to, for example, 200 iteration max. This is iteration max. So you're starting from 1.2 at iteration 1. At iteration 200, you reach 2.4. So this is the maximum value at the first iteration, and this is the minimum value at the last iteration. And you can decrease this omega linearly. So you can have omega of t or W of t equal to W of t minus 1 minus this increment. يعني this increment is 1.2 minus 1.4, 1.2 minus 0.4 over 200. So at each iteration, you reduce the omega or W, the inertia, by 0.8 over 200. So each iteration you decrease the omega as such. So omega is the maximum, which is the initial weight, typically, and omega minimum is the minimum or final weight, typically 0.4, and you can have such a decreasing function here. This is omega max and this is omega min. At any iteration here, you can find how much the W. And by applying in this as an updated rule for omega. Okay, any question? If you have any question, please don't hesitate to ask.
Yes.
Yes, go ahead, Nasser.
For n, as n goes small, for example, 5, mean I'm increasing my steps. So my velocity will, my value will jump to a far position.
Yes.
So is it good that if we set in the beginning, we set it to the 5 rather than to make it a 10, which is the optimals, or 8, and then after a couple of iteration, and then I set it to where I got the most preferred place. For example, I'm looking to north to the east, and then I got that place is good values indication, and then I decrease the step to n is equal to 15 or 20.
You are right. You can do this. Yani you can have n adaptive. Yani you can start with n small to allow for the particle to fly for far positions, and while the search progressing, you can start reducing n. You can do this. You can have n here as an adaptive, similar to the inertia, exactly similar to the inertia. Okay.
Okay.
The inertia, we start with the initial inertia, and we update it every iteration. We can do this also here. And you can have at each مثلا 10 iteration, you can decreasing n by 1 or sorry, increasing n. You start with n equal to 2 or 5 or 4, and then you n equal to 5, n equal to 6, 7, 8, 9, 10. So you reduce the intervals or the size of the interval, or you reduce the Vmax while you are approaching the final stages of your search. You can do this. You can implement it.
Okay, thank you.
And this is the beauty. I think you now experience in MATLAB where you have like built-in function of GA, and you feel you are very tight. The situation is very tight. You cannot implement your idea. If you have such idea, you can implement it easy if you develop the code by yourself. And this is what I was asking the students before in previous terms, to develop their codes. And actually, to be frank with you, if you develop only one code, you will find yourself just developing other codes very simple. You have similar, operators, similar steps, initialization, stopping, and all this. If you can develop one code and you can access it, so you can implement such ideas to make n adaptive, to make to check any idea. You can do it. But with the built-in functions, I don't know whether you can investigate and you can get the M code of these functions and you can play with. It becomes a little bit. Okay, so this is the inertia. Do you have any question? Other question?
For me, thank you. No.
Muhammad Tahir? Yes.
Yes, Doctor.
Yes.
A small question is regarding this inertia. It's two methods, either with alpha or the linear decreasing, right? Which one is usually used?
Well, actually, usually in literature, you will find this, which is linearly decreasing. You will find this one in literature, and when you read. And actually, for me, my personal experience, I applied both, and I found this more. I don't to say no much better than this. No, they are somehow the results are comparable. But you can find this in literature widely used. This one.
Okay, thank you.
Okay. So this is the inertia. Another term that is usually used here in particle swarm, what we call the individual best, or sometimes you call it local best, or sometimes we call it particle best. So this is the best position for the particle based on its experience. And the particle moves here in the search space. The particle is moving this way. You have another velocity, and this is the position here and there and so on. Definitely, at each position, you are calculating the objective function. For this position, you have the objective function. For this position, you have the objective function, and so on. So the particle can assign what is the minimum objective, or what is the best position that this particle visited so far. So you can have the particle is here, but the best position was there. This is the best position for the particle. It visited this one, but in the second iteration it moved this one, but still the particle remembers its best position. Okay, its best position. This is the individual best, or local best, or particle best. And each particle, if you have 50 particles, for each particle, each particle remembers its best position. So you have 50 of individual bests, or 50 local bests. Okay, so each solution or each particle will remember its best position, which we call it particle best, or local best, or individual best. So this is the best position. As a particle moves through the search space, it compares its fitness value at the current position to the best fitness value it has ever attained at any time up to the current time. History. Memory. You have a memory here. So you memorize the best position. So this is also another advantage of particle swarm. You know, it has like a flexible memory for the particles to remember where the best position. So the number of individual bests, as I mentioned, it is equal to the number of particles. If you have 50 particles, you have 50 individual bests. The best position that is associated with the best fitness encountered so far is called the individual best, which this is the best position, X is a position, and V is a velocity. And for each particle in the swarm can be determined and updated. X star, we call it X star here. So for each particle, the particle best can be determined and updated during the search. Of course, during the search, you are update the best here. Okay, yani here at the beginning, when you start at the beginning, you consider this is the best. When you move here, you compare the objective with this one, and probably this is still the best. The initial is still the best. And you update the velocity and you move to another position. You calculate the objective, you compare the objective with the best stored, and then you update the best here. And then when you move, you calculate the objective here, you compare this with this one. Probably if it is minimization, the objective at that position is greater than this, so you keep the best as it is. So for each position, you have to update the local best or the particle best. I hope no things are clear. In a minimization problem with the objective function J, the individual best particle xj star of t is determined such that you can have the objective J star. So J star is the local best position or objective function for the best position. So if J of the local best star here refers to the best. If the local best is less than the objective of the current position, what should we do? What do you think? Think about it. If the objective of the best position is lower than the objective function of the current position, so what should we do? Should we update? Should we neglect? What should we do here? Any answer? Okay, so of course we need to update the local best, but if the objective of the local best is lower than the current position, so we keep the local best as it is. J here becomes J star, the local best, and equal to this. And you have here the objective function here is lower than, assuming this is the minimization problem, and this is for all the iteration before this one. For simplicity, assume that for jth particle individual best can be expressed as, and star here refers to the local best or particle best or individual best. Then we have x double star. This would be kept for global best and also the global best objective. Okay, global best x double star. X double star is the global best solution. How many global bests do we have? How many global bests do we have in the population or in the swarm?
One.
Yeah, of course, it should be one. Number of particle best is equal to the number of particles. But here we have only one solution that gives you the global best, which is one among the one which is among the particle bests. And if you have all the particle bests for particle 1, particle 2, particle 3 up to particle 50, you have the best solutions. One of those will be the global best, yani best of the bests. Okay, so this is the global best. It is the best position among all individual bests positions achieved so far. This is the global best. This is what we are looking for, actually. We are, when we solve the optimization problem, we are looking for the global best. The global best can be determined such that the objective function of this one will be lower than the or equal to the objective function of all the local bests. J here from 1 to n, all the particles. So one of those particles will be the global best. For simplicity, assume that J double star an objective function of the global best. The X double star is the position of the global best. This is the position of the local best. Okay, now these are the terms. Let us see how to run the particle swarm optimization. What are the steps for the particle swarm optimization? From where we can start and how to move from one iteration to another, how to create the other positions or the updated position, how to update the velocity, and how to update the local best and the global best stopping criteria. All these steps will be discussed here. Yes.
Doctor?
Yes, go ahead.
Assuming that we have a population of, for example, 50, and we have K and T1, T2. And then the velocities mean that we are moving by a certain step in certain direction.
Yes.
And we are learning this direction is better than the other direction. This is what I am understanding. Is it correct?
It's not direction, it is position.
Yeah, the positions mean the values. If it is in 3 dimensions, mean the position. If it is K and T1, T2, it mean the values of these parameters.
Yes.
Yeah, so is it better to move all at once? Or for example, I'm just having the velocity for the K and then fixing a certain time the T and T1. For example, I'm seeing that this is the optimal for T1 and T2, and then should I move only in one direction?
Actually, this is X1. This is the first particle. And each particle has its own velocity. So assume that V1 is equal to -2.05 minus 0.1, for example. These are the velocities of the particle. Okay? Is it clear, ya Nasser?
Yes, clear, doctor. But what I mean that if after 5 iteration, I'm reaching, for example, the 0.1, just it's becoming, for example, 0.3, and then for the 20 is reaching, for example, 10. Shall I stop at 0.3 for the T1, and then I still moving in the K and the T2, for example? Or I'm just keeping the same velocity for all iterations?
No, velocity is updated at each iteration.
So I can change the 0.5 for just one genes and then increase the others.
Yeah, of course. At each iteration, you update the velocity. You have new velocity at each iteration. Okay?
Okay. Because I thought that I should maintain the same rate. For example, if I increase twice, and then I should increase all the twice. If this one is 4, the other one should be 0.1, for example.
No.
Okay, that's clear now.
Okay, so velocity will be updated at each iteration. The position will be updated at each iteration. And then based on these updated values, you can calculate new and you can update and so on.
They are independent.
What is not updated is the Vmax. Vmax is constant. Once you define a number of intervals, when maximum of the K or T1 or T2 maximum and minimum are known, and you set n equal to 10, for example, in this case, the maximum velocity is fixed. Maximum velocity is fixed. Okay? And you have to look at the maximum velocity. When you update the velocity, in the next iteration, you may find the velocity, مثلا, in the dimension of K equal to 12, while this velocity of K maximum equal to 10, the 100, for example, over 10. So the maximum is 10. And when you update the velocity, you find it out equal to 12. In this case, you have to stick with The maximum velocity is 10. The velocity is updated at each iteration, but the maximum velocity you have to observe it. Okay.
Okay. Thank you.
And with the iteration or steps, this will becomes clearer, inshallah. In the particle swarm algorithm, the population has n particles or candidate solutions. So we have n particles, 50 or 100, usually with a small size, and n usually between 10 and 50. You can have it. طبعا compromise is there. If you have 10, then you have slow conversions. If you have 50, of course, you have fast conversions, but the iteration time will be, of course, definitely higher. You are handling now 50 solutions. Each candidate solution has m-dimensional real valued vector, real optimized parameters. The particle swarm can be described in the following steps. The first step is initialization, which is the same as other techniques, GA, differential evolution programming. You start randomly where you have for each dimension, K with T1 with T2, you have minimum and the maximum. Then you can scatter the solutions within maximum and minimum. So set the time counter equal to 0 or iteration counter and generate randomly n particles, x1, x2, x3, x and so on. These are the genes or the dimensions here, and randomly selecting the uniform probability over the search space, maximum and minimum. So you can have each gene for each particle, minimum plus a random number between 0 and 1 of maximum and minimum. So nothing new for the initialization step. It is similar to this. In addition to position, in addition to the particle here, you also initialize the velocities. In velocities, you generate randomly initial velocities of all particles. يعني انت عملت هناك 50 solutions, you generate also here 50 velocity. You have solution 1, velocity 1, solution 2, velocity 2, and so on. So you generate here the randomly initial velocities in all particles. Of course, the limits here is V max and V minimum or minus V max. So Vj for particle j in dimension k generated by randomly selecting a value with uniform probability over this. So you can easily write this value. Velocity of each particle equal to minimum velocity, which is minus maximum, plus random number between maximum and minimum. So you can generate the velocity similar to the position. You generate also 50 velocities for the population. Each particle in the initial population is evaluated using the objective function. Of course, you have the position for each one. The position or solution. If you have the solution, you can calculate the objective function for each solution. Solution 1, this is J1, and the solution 50, you have J50. Okay? So, of course, you can get the minimum, you can know the best, the global best, and each solution here will be at the beginning. We will keep it as the local best. Also for particle number 1, the position that we have is the particle best or individual best at the time being. So all these solutions will be considered as the local bests, and these are the associated objectives. And then one of those will be selected as the global best, J double star, which is the minimum out of those. And of course, the global best solution also can be selected out of those, corresponding to the minimum objective. So you have now the local bests, and also you have the global best. Is it clear? This is from the initialization step. I think, yes, here it is. For each particle, we consider the local best equal to the particle itself, and this is the initial, and the associated objective equal to the objective itself. And this is the initialization step, and you can select the best value of the objective, and J best, the J double star, and this also the position can be extracted, X double star. We need the local best and the global best in updating the velocity later on. And when you update the velocity, of each particle, this is the search space, the particle is here, and after some iteration, for example, this is the local best. This is the local best, and here is the global best. This particle with this current position will update its velocity based on the local best and also based on the global best. So it will look at the cognitive part, its own experience, and also it tries to adjust itself towards the global best, which is the social part. So you have to keep local best and the global best defined here. So we define here local bests and the global best as such. Set the initial value of the inertia weight, W of 0, and as we mentioned, we can have it equal to 1.2, for example, 1.3, 1.4. And of course, you can have initial solutions scattered randomly around the search space. And at the same time, you can inject some of the solutions. This is also can be done if you have better solution, if you have from your experience, from previous experience, you have the good solution or better solution. So you can inject them in the population as well. And you can inject them intentionally. In some cases, you don't need to start randomly completely. You have N population, you start not randomly with all N, but you can keep, for example, if you have 5 solutions and you know these are the good solutions, so you can generate N minus 5 randomly and 5 all the solutions. So this will enrich, of course, the search or guide the search. It will, reduce the number of iterations, or it makes the conversions faster. So you can have also additional solutions if you have, and definitely also you need to initialize the velocity for each particle. So you initialize the velocity for each particle as such. Okay. At time update, of course, you increase the number of iteration, t equal to t plus 1, and then you update the weight. You have the initial weight is already known. Update the inertia weight, having this or having this, and t equal to 2 here, alpha equal to, you set it equal to 0.9 or 0.95, and this is the initial value you have, and all this is parameters known, so you can update the weight. And then we will go to the major step in particle swarm, which is the velocity updating. This is the major step in particle swarm. Updating the velocity using the global best social part and the particle best, the cognitive part, the individual best, and also the old or previous velocity of the particle, and then you update the velocity as such. The velocity at the iteration, current iteration, equal to the velocity of the previous iteration multiplied by the inertia, which is updated already, and plus the cognitive part, where you have the difference between the current position of the particle and its local best. And you multiply this by a random number between 0 and 1 and the constant C1, which is usually set equal to 2. So this is the cognitive part. And you have another term, which is the social part. So you compare here, or you get the difference between the current position of the particle with the global best that we have. R2 is the random number between 0 and 1. C2 is constant. Usually we have it equal to 2. Y2 we will see. And this is, of course, will be repeated for each particle, for each dimension. And this is for dimension K. Velocity of dimension K and all these positions of the K optimized parameters. For T1, we will repeat this. For T2, we will repeat this. Okay? And C1 and C2 equal to 2. When you have here R1 between 0 and 1, if you have it 0, if R1 equal to 0, that means you have you eliminate this cognitive part, which is very rare. R2 equal to 0, you eliminate also the social part. Usually R2 is around, for example, 0.5. So if it is 0.5 multiplied by 2, 0.5 multiplied by 2, that means when you put most likely the weight of the cognitive part, and this is the weight of the social part, and this is the weight of the cognitive part. And if you most likely will be almost the same. So you have same level of importance of the cognitive part and social part. Of course, you can increase C1 equal to 2, 3, 4, 5, more than C2 if you want to stress more on the cognitive part. And of course, you can also increase C2 higher than C1 if you want to emphasize more on the social part. But usually in the literature, you will find C1 equal to C2 equal to 2. And you have equal importance of the cognitive part and social part. Any question? This is the major step in particle swarm, velocity updating. C1 and C2 are positive constants typically. C1 equal to C2 equal to 2. R1 and R2 are uniformly random numbers in between 0 and 1. طبعا this random number is created or generated at each. When you call, you generate another random number, different random number. So this is the cognitive part, and this is the social part. Any question?
Yes, question.
Go ahead.
Yeah. Now, if I ask about the dimensions, the VGA.
The dimension
Yeah.
of what?
The VJK.
This one.
Yes.
This is a scalar value.
Yeah, but if we run it across T right now, it will be like because I can see that the jth particle velocity in the kth dimension. When we said kth dimension.
Yes, in the k dimension. Yes.
So when we run it with T, because we will run it for several T, and then
T is a number of iteration. يعني T is a number of iteration or number of generation.
yes.
يعني انت you start here يا فوزان, you start with x, okay, x0, x of 0 initial and v of 0.
Yes.
So this is x0 and this is v0, right?
Yes.
Right. This is v, if this is x1, this is v11, this is v12, this is v13. Okay, so this is the velocity of the particle 1 in dimension 1, second dimension, third dimension. So if you have here x, yeah, طبعا, of course, and I can give you numerical example, but you know, I mean, this will again at the beginning this x star will be x1 of 0, but assume no, this is at any iteration t or t minus whatever t. So this is x position or the local best. For example, it is 18.5 and 0.2, and the global best, this could be, for example, 25.1 and 0.7, whatever. So this is the particle of the current position at iteration t, and this is the velocity at iteration t, and these are the local best for this solution, and this is the global best for the whole population, right?
Okay.
So what we will do is we'll do the following. We need to, assuming that in omega of t equal to, for example, 0.8 or whatever. Okay. So v of t plus 1, next iteration.
Yes.
Next iteration. This is equal to, of course, here you can do it by for loop from 1 to number of optimized parameters, m, right? You can do this, or you can do it in vector form, and you can have it in vector form. You can have this x as a vector, the xj 1, 2, 3, and we have here 1, 2, 3 also. Vector is 1, 2, 3, 1, 2, and so on. And it's up to you. You can have it at each dimension. You have here m or vi of t plus 1 equal to 0.8 multiplied by base velocity, all the velocity, layer 2. This is the first part, plus C1 R1 multiplied by, this is the best position, which is 18, minus the current position, which is 20. So 18 minus 20 plus C2 R2 multiplied by X double star, which is 25. 25 minus the current position, which is 20. Okay, so this one in the dimension of k. This one would be in the dimension of the first gene or the first parameter. So this is V1, and if this is you know, you can have for loop طبعا, بس طبعا the values دي will be different. يعني this one will be here, for example, the velocity here will be 0.3. This one will be 0.8, and this one will be 0.5 and the minus 0.8. 0.1 minus 0.8. I have this here. V in the third dimension, and so on. You have a V in T1, you have a velocity in T2 dimension. So if you calculate these three values, then you get the V2. Now V2 is, you have it here. Okay, so this is the updated velocity. This is the updated velocity. واضح يا فوزان ولا مش واضح؟
Yes. I'm trying to link, Doctor, the M here to K.
The K varies from 1 to M. لأن ال K اللي هي الدايمنشن. الدايمنشن starts from 1 to 3. So the K is from 1 to M. This is the, you can have it here K. K from 1 to M. إنما ال I, إنما ال J, ال J هي ال particle number. This is the particle number. يعني ال J ديت لو بنتكلم ال J دي varies from 1 to إيه؟
N.
To N. The J varies from 1 to N. So, and the K varies from 1 to M, the number of optimized parameters. Is it clear?
Yes, clear.
Sorry, Doctor, I have a question, if you allow me.
Yeah, please go ahead.
Can we say that the velocity will decide the direction of the swarm?
Yes. As we will see in the next step, after velocity updating, we will see the position updating. Okay? يعني here, طبعا we have to check the velocity limit. And sometimes when you calculate these values, 0.8 multiplied by 2, this is 1.6, and this is 2 times 1, for example, with minus 2, you have minus 4, over here, and then you can find out, this is مثلا greater than V max or lower than V minimum, minus V max. So in this case, you have to limit the velocity. And you put it at the violated limit. Okay, so you have to check the velocity limits, and you have to fix it. If the velocity violated its limits, set it at its proper limit. And if it is greater than V max, you set it at V max. If it is lower than V minimum, you set it at V minimum. Okay, it is worth mentioning that the second term represents the cognitive part, and the third term represents the social part, as we pointed out. We have here the current position, and this is the best position, particle position, my best preference, or the particle best, individual best, and this is the global best, neighbors. This is the global best, and this is the current velocity. So what you will have, you have the weight multiplied by this velocity. So you go in this direction for a certain value. And then you have a part which is related to the difference between the current and the local best. So you have a component in this direction, and you have also difference between this and the global best, and you have a component in this direction. So in this case, you can end up with the updated velocity. This is the first term, the weight multiplied by the current velocity, and then you go a second component will be, in this parallel to this, difference to this, and then the third component, the third term of the velocity will be like in this direction, which is parallel to the difference between the global best and the current position. So this is now the updated velocity. So this is the velocity now. This is the summation of the three gives you the updated velocity. And then you update the position. The position update is based on the updated velocity. Each particle changes its position according to the following equation. It's very simple. A new position equal to the new velocity plus the current or the old position. So you update the position accordingly. باعتبار ان velocity multiplied by the time equal to the distance or the whatever. Time هنا one iteration by one iteration. So this velocity plus the old position gives you the new position. Is it clear? Any question? طيب, now we have new position. So we can calculate the objective function corresponding to the new position. And we can update the individual best if needed. We will compare the objective function of the new position with the objective function of the local best, and then we can update the local best accordingly if needed. So each particle is evaluated according to the updated position. You calculate J, and if J of the particle new position less than the local best. If it is less than the local best objective, in this case, you need to update the local best. So you set this value as the local best and the updated position as the local best position. So you assign X star, you forget about the old one, and now X star equal to the current position, and the J, the objective function of the local best, equal to the objective function of the updated position. If no, then you skip this and go to step number 7 directly. You don't need to update the individual best. So else go to step 7 directly without updating. Okay, and you end up with a position which is not better than the local best. Type, we update all the best positions. So the next step is to update the global best. Global best updating. Check or search for the minimum value, J minimum, among all the local bests, and get the solution corresponding to J minimum, and you set it as the global best. So if J minimum is lower than the global best, then updating the global best as X double star, position of the global best equal to the X corresponding to the current solution, to the solution of the minimum objective, and you have this. And then you go to step 8. Else, if this is not the case, you go to step 8 directly without updating the global best. I hope you are following. The stopping criteria is similar to what we have earlier. Number of iterations since the last change of the best solution of global best, let us say. Global best. Solution is greater than a specified number. And then you can come here and ask, هل J minimum is lower than J double star stored corresponding to the best solution? J minimum calculated lower than? If yes, then you will update the best the global best, and then you can set K best, this is a counter, equal to 0. Else, you have a K best equal to K best plus 1. So either you update or you go directly to the next step. So here, once you update the global best, you set the counter to 0. If you don't update, then you can have the counter is increasing one after one and so on. So, and then when you go to the stopping criteria, you can ask whether this K best is greater than or equal, for example, 20 iteration. With 20 iteration, if the K best reaches 20, in this case, that means no, this solution doesn't change for 20 iterations, so we can stop the search. So this is how to implement this simple criteria here. So if the best solution doesn't change for long time, 20 iteration, we can stop. The other stopping criteria, which is the classical one, number of iteration reaches the maximum allowable number. So this is the steps of the particle swarm. Do you have any question? Do you have any question?
Yes, I have a question.
Yes, please, go ahead.
Actually, the swarm optimization, it's work in 2 stages, which is global and local search. Can we say that it is deal with them as a separate stages?
No, it is not a separate stages. It is not separate. At each iteration, a local exploration where global exploration are embedded. So it is hybrid. It is not sequential. And they are not separate. They are hybrid together.
The other question. Yes, I get the point. Can we control the both stages at the same time?
What do you want? What do you want to say? And how to? What do you have in your mind?
Actually, I wanted to compare it with the genetic algorithm. I think the genetic algorithm to have the same, procedure that it want to go through the global and local stages, to find the global based on the population size. My point is that what is the difference between these algorithms mainly?
In genetic algorithm, do you carry out the crossover? For example, we have crossover and mutation. In crossover, are you looking to the global solution or optimal solution, or you are given two parents and you do crossover among the parents, whatever the parents are?
The second one.
So that means no, it is not directed toward the global best. And also in mutation, you carry out mutation without considering any of the good solutions or bad solutions. And you do mutation blindly. Okay? But here, when you update the velocity, you are updating the velocity considering the global best and also local best. So it is different than genetic algorithm here. Okay. Do you see the difference between the particle swarm and the genetic algorithm?
Can we say in the other word the swarm optimization will will save the previous best solution, then we'll update on that?
This is another, as I mentioned, this is another difference between particle swarm and the genetic algorithm. You have some kind here of memory, and the search has a memory. It remembers the best position that is visited before. In genetic algorithm, you don't have such memory. Each solution will, each parent produce a child, and there is no relation between this child and the parents. And when you have a mutant, or if you do mutation, you have, and you are not saving the positions of the solutions created earlier. This is also another difference between VSO and genetic algorithm. Memory, local and global search capability of the particle swarm, unlike GA. Yeah, this is the some of the differences between particle swarm and GA.
Sorry, Doctor, can we say that at the end, the particle swarm algorithm will lead to or will converge faster than the genetic algorithm?
You can, طبعا احنا we are, we don't want to generalize things. For each problem, for a specific problems, and I mean, usually in optimization literature, you have some of the benchmark problems for optimization, very difficult optimization problems. And when you develop a new technique, you test the technique against these standard optimization problems, and you can see the comparison between them in terms of number of iteration, number of objective evaluation, computational time, solution quality, robustness of the technique. You run it several times and you see the variation among each run. And you can have some comparison aspects here. Usually, or most likely, the particle swarm will behave better than a genetic algorithm. This is you can find it in literature and also based on my experience. Is it okay, Hisham?
Yes, alhamdulillah, it's okay. But the last question about the particles movement, they will move in the same direction, or we can move each particles in different direction?
Different direction, definitely. Each particle has its own velocity. This particle is moving this way, this particle is moving this way, and then it comes here, and then this comes here, down here, and so on. So different direction, definitely. You can see from the velocity, when you have the velocity here, with these terms, you can have these values will definitely, you have its own best and also the global best. With the current position, you may have this is minus sign, you may have this is positive sign, minus, and so on. So the velocity could be 2 or minus 2, minus 3. So in opposite direction, and this is plus 2. In this way, the minus 3 will be in the opposite direction, and so on. So for each dimension, each particle has its own velocity. Any other question?
Thank you, Doctor. It's clear.
Okay, thanks. Any other question? I think this is the time now. Is over. Let us stop here. We have only 2 slides or so on this, and we will cover them in the next class, inshallah. Today I was preparing a quiz actually.